In section 0.4, I will be discussing the common mathematical relationships that you will see this year in physics and scaling problems. Be sure to watch these videos that will be linked on Schoology. One of the main goals of physics is to describe how a change in one quantity will affect a change in other quantities. If the relationship between two quantities is already known, then you'll be able to predict how changing the value of one quantity will affect another quantity. This is referred to as scaling. This table shows the most common relationships that you're likely to see in physics this year. The leftmost column shows the names of the relationships. The middle column shows the general equations that are associated with each relationship. And the rightmost column describes the shape of the graph that's associated with each relationship. I'll go through each relationship throughout the remainder of this lecture. The most basic relationship between two variables is a direct relationship. This can also be described as a directly proportional relationship. We will use the symbol that kind of looks like a fish to represent is proportional to. The value k that multiplies the independent variable x is a constant or a combination of other constants and is known as the constant of proportionality. It'll also be equivalent to the slope of the graph that's associated with this relationship because the graph is going to be linear, but it's going to be linear that passes through the origin. An example of a direct relationship that you're already familiar with is the circumference of a circle. You can see that it matches up perfectly with the general form of a direct relationship, and that the constant of proportionality, k, is equivalent to 2 pi. You can recognize that two quantities share a direct relationship if one quantity is multiplied by some number and that the other quantity is then multiplied by that same number. For example, if x is doubled or multiplied by 2, then y will also be doubled or multiplied by 2. The equation that shows a direct relationship is mathematically equivalent to the statement that the ratio or fraction of the two quantities is equal to a constant. This fact is important because you can use this to set up what I call a scaling equation. If the ratio between variables is always equal to the same constant, then the two instances of that same ratio will also be equivalent. You'll see this in action on the next example. The example on the next slide will show you how to use scaling to predict a new value. You should note that scaling is only possible if the equation can be rearranged so that it is written as a ratio or product of two quantities. You're unable to do this for polynomial equations or equations that have a plus or minus. And you can follow these steps to set up a scaling or proportional reasoning type equation. First, you'll need to find the equation. That's where the physics will come in. Second, you'll need to manipulate the equation and move all variables to the same side and all constants to the other. Third, you can then use our scaling equation based on the variables that are on one side of the equation, and then you can use that equation to solve for your unknown variable. This example will show you how to use scaling to predict new values when you know the relationship between two quantities. For hourly employees, the money earned in a weekly paycheck is directly proportional to the number of hours worked in a week. In this example, we'll consider an employer that pays $800 for 8 hours of work. Part A asks, how many hours would you need to work to earn $200? Well, you may be saying to yourself, if I want to earn twice as much money, then I'm going to have to work twice as many hours. And you'd be correct in saying this because your paycheck shares a direct relationship with the number of hours worked. However, I'm going to show you how to work this out using scaling so that you can determine the number of hours you need to work to earn any amount of money. When two quantities share a direct relationship, that's equivalent to saying that their ratio is always equal to a constant. So we can say that a constant is equal to your pay P divided by the number of hours worked H. And we can use this to set up a scaling equation where that constant is going to be P1 over H1, and it's also going to equal P2 over H2. The pay to hours worked is always the same constant. Next, we can insert the three known values into our scaling equation, P1, P2, and H1. Next, we can rearrange the equation to solve for the unknown value H2, and then we arrive at our expected value of 16 hours. Part B asks us to calculate the value for the constant of proportionality for this relationship and to identify its meaning. The constant of proportionality for a direct relationship is simply the ratio, or in this case, pay divided by hours. $100 divided by 8 hours is $12.50 per hour. And hopefully you recognize this as your hourly pay rate. It's important to realize that the constant of proportionality will almost always have some important meaning. In this example, we will use scaling in the context of something that you learn in chemistry. Charles' law describes the relationship between the volume and the temperature in a gas at a constant pressure. Charles' law says that the volume in a gas is directly proportional to its temperature. Part A gives us a volume and a temperature and asks that we calculate a new volume at a different temperature. We can use scaling to set up an equation to predict this new volume. Because the relationship is described as directly proportional, we know that the ratio of volume to temperature is a constant. From this, we can form a scaling equation. Next, we can insert the three known values. Then, we can rearrange the equation to solve for our unknown value, V2, which yields our answer of 6.3 liters. Part B asks us to examine the ideal gas law to find the meaning of the constant of proportionality for Charles' law. In Charles' law, volume and temperature are considered to be the variables, and therefore N, R, and P must be considered to be constants. If we rearrange the gas law to group the constants on one side of the equation and the variables on the other side, then it yields this result. We can see that on one side of the equation, we have the ratio of variables equaling a group of constants. The fact that we have a ratio of variables equaling a constant, that is our signal that volume is proportional to the temperature. And the group of three constants on the right-hand side are what we call the constant of proportionality, K. If you remember that R is a constant value, then you could solve for P if you knew the value of N, or you could solve for the value of N if you knew the value for P. The next relationship that we must discuss is a linear relationship. We can describe this relationship as y is a linear function of x. Because the equation contains an addition, you're not able to use scaling for quantities that share this type of relationship. Here, the value k is described as the slope of the graph, while c is the vertical intercept of the graph. So this value on the graph is equal to y is c, and the slope of this graph will be equal to k. An example of this relationship is the velocity of an accelerating object at a given time. This relationship, if it were to be graphed, would give you a linear graph with a y-intercept equal to the initial velocity of the object, and it would give us a slope equal to the rate of the acceleration for the object. When the equation describing a relationship between two variables shows the independent variable x as squared, then we describe the relationship as a square relationship. We can state this in two ways. We can say that y is proportional to the square of x, or we could say y is proportional to x squared. Both are acceptable. The graph shape that's associated with a square relationship is a top opening parabola. Top opening means that it curves upwards as opposed to sideways. An example of a square relationship is the relationship between the area of a circle and its radius. You can see here that the equation for a circle matches perfectly with the general form of a square relationship. A square root relationship is one where the independent or x variable lies underneath of a square root. We can say that y is proportional to the square root of x, and alternatively, we could say that y squared is proportional to x. Sometimes this description, the y squared is proportional to x, is preferred because then we don't have to deal with units that contain a square root. We usually prefer whole number exponents to roots when expressing our units. We'll talk more about this in the next lecture when we discuss the linearization of graphs. The graph shape associated with this relationship is a side opening parabola. An example of this relationship is the velocity of an accelerating object as a function of the distance that it travels. Notice that the d is underneath of the square root. We can write the equation just a little bit differently to show that this matches up with the general form of a square relationship. If an increase in the value of one quantity causes a proportional decrease in the value of another quantity, then the two quantities are likely sharing some sort of inverse relationship. Notice that in the general form of this equation that our x variable ends up in the denominator. You can recognize that two quantities are inversely proportional when one value is multiplied by some factor, that the other value is then multiplied by the reciprocal of that value. The graph shape associated with an inverse relationship is called an inverse curve. An example of an inverse relationship is the velocity and time for a trip of the same distance. If you travel with twice the velocity, then it takes you half the time to reach your destination. The final relationship that we will discuss is called an inverse square relationship. This relationship shows up all over the place in physics. However, we're really only going to encounter it when we discuss gravity at the end of the year. The graph shape associated with this relationship is also an inverse curve. It's impossible to visually distinguish between the inverse curves for an inverse relationship versus an inverse square relationship. And this is where linearization is going to come in the next lecture. An example for this is the force of gravity between two masses that are separated by some distance d. Here's the equation for that relationship, and you can see here that it matches up with the general form for an inverse square relationship. In this example, we are going to decide the relationship and graph shape for several equations. In part A, the main thing to notice is that our variable x is squared. I can write this just a little bit differently to highlight how it matches up with the general form of a square relationship, where we have y is equal to k times x squared. So the relationship is a square relationship, and the graph shape that's associated with this relationship is a top opening parabola. In part B, you should notice that the variable x is in the numerator and it has no exponent. This suggests that we're going to have a direct relationship. Again, I can write this just a little bit differently so that you can see how it matches up with the general equation for a direct relationship. y is equal to k times x. So this is a direct relationship, and the graph shape associated with this is a linear graph that passes through the origin. In part C, you should notice that we have a ratio of y squared to x, and that's equal to a constant. Whenever we have a ratio equal to a constant, that implies that the numerator is proportional to the denominator. So here this is going to suggest that y squared is proportional to x. And we can write this just a little bit differently, and we can write it just a little bit differently again. And this way it's a little more clear how this will match up with the general form for a square root relationship, where we have y equals k times the square root of x. So this is a square root graph or square root relationship, and the graph shape is going to be a side opening parabola. For part D, we want to notice that we have a product of y and x, as opposed to a ratio that we saw in part C. Whenever you have a product equaling a constant, that's a signal that you have an inverse relationship. We can rearrange this equation to solve for y, and now you can see that we have our general form for an inverse relationship where y is equal to our constant k divided by x. So this is the same as that general form. So this is an inverse relationship, and the graph shape associated with this relationship is an inverse curve. In part E, you should notice that our x is squared, and it's in the denominator. That should be a signal to you that we have an inverse square relationship. And this shows how it matches up with the general form for an inverse square relationship, that's y equals k over x squared. Here k is this combination of constants a over b. So we have an inverse square relationship, which will be represented by an inverse curve. In part F, the equation shows that x is located in the numerator, and it also has no exponent. So that will mean that it's either a direct or a linear relationship. And this one's going to be a linear relationship because of the subtraction of this constant. Direct relationships don't have a plus or a minus in them. So that is going to make this a linear equation or a linear relationship. And you can see that this matches up with the general form for a linear relationship, where we have y is equal to k times x, and then plus some constant. Here it's minus c, but the general form is plus some constant c. So the relationship is linear, and the graph shape will be linear, where it has a slope equal to a, and it will have a y-intercept equal to negative c. So it will look something like this, where the y-intercept is equal to negative c, and the graph has a slope equal to capital A.